So hi guys, today's question is implement stack using queues, right? Now basically what the question says, it's a design question. So we need to design a class called myStack, which works as a stack, right? The stack data structure. But we can only use queues in the internal implementation of this class. So in all these functions, the only data structure that you can use is a queue, right? And so these are the functions that your MyStack class should have. Obviously, it should have an initialization function, that is your constructor, and then it should also have a function called push, which adds an element to the stack, a function called pop, which removes the top element of the stack, a function called top, which just lets you peek at the top element of the stack. So yeah, but it doesn't remove it from the stack. And a function, boolean function called empty, which returns true if the stack is empty and it returns false otherwise. Okay. Some notes here are that we can only use the standard operations of a queue. So that means that we can push to the back of the data structure or peek slash pop from the front. We can also find the size of the queue in the internal implementation and use something like is empty if we need to use that. So it also says that we can simulate a queue using a list or dequeue if our language natively doesn't support a queue. So since I'm coding in Python, I'm going to use a dequeue. Uh, but yeah, before we get into the implementation of this, uh, let's discuss a few things. So here the question says that we need to implement this stack using only two queues, right? But that's not what I'm going to discuss in this video. I'm going to actually discuss a more involved problem that is given as a follow-up here. So this follow-up says that we need to implement the stack using only one queue, right? So I'm going to try to code this part up, and so let's just shift to the blackboard to see how we can implement a stack in fact using one queue.
Uh, okay, so like I said, let's see how we convert this single queue into a stack, right? So let's consider the push function here, right? So a push function in a stack, what that does is that it adds an element to the top of the stack, right? And a push function of a queue, what that does is it adds an element to the back of the queue, right? In both cases, the front or top of the data structure is where the element is removed from. So if we go by that condition, a stack will add an element to the top of the queue because it's a last in first out data structure, right? And a queue will add an element to the back, okay, because it's a first in first out data structure, right? So so how do we push into this queue such that it works as a stack, right? So imagine there are some elements already in this queue, let's say 2 3 7. They don't need to be in sorted order, so let's say there's one also, right? And now I need to add a new element called 5, right? And yeah, so what I want is that when I add this 5 to this queue, it should actually come at the top of the queue, right? If I want it to work as a stack, I want this 5 to come at the top. This should be the first element when I use a pop on this queue that gets returned, right? Gets taken out. So how do we do that? The first thing that we can do is just add 5 to the back of the queue, right? So we add 5 to the back of the queue here, and now all we do is that we circle all these elements back one by one, right? So first we circle 2 back. So what that does is it just shifts 2 to the back of the queue. right? And the next thing we do is we circle 3 back. So this shifts 3 to the back of the queue. And the next thing we do is we circle 7 back. So this shifts 7 to the back of the queue. And the next thing we do is we shift 1 back, right? So this shifts 1 to the back of the queue. And so our new queue becomes this 52371, right? And this is what I wanted, that the element that I'm currently adding to my data structure should actually be the top element, right? The front element in a stack. But when I use a push to the queue, it adds it to the back. So what I did was I just circled all the elements that were in front of it to the back of it, and now this element has become the first element here, right? If you see this carefully, this process will if we do this process carefully for all the elements that we add to the stack from the beginning, then this will act as a normal stack, right? So what I mean by that is that right now when we added 5, we actually added it to the back of the queue, right? But because we wanted this to work as a stack, we shifted all these elements back one by one, and now 5 is uh, at the front, right? So it looks like this works well for this 5 element, but how do we know that it works well for the other elements that we add? So say I want to add 6, right? Say or let's say I want to add 12. I want to add 12 to this stack. So I'll repeat this process again. First I'll add 12 to the back of the stack, and then one by one I'll just add all these elements. I'll circle them to the back. And what do I mean by circling them? I mean that I'm popping it off, storing it in a variable called a, and then I'm appending this variable, pushing it to the back of the queue, right? So when I do this, what I'm left with is that I'll have 12 here, then 5 behind it, and then 2 behind it, then 3 behind that, 7 behind that, and 1 behind that. So in the end, I'll be left with this. Just 12 in the front got added to whatever was behind in our data structure before, right? And this is what a stack is, right? Anything that gets added just gets added to the front of the stack, and everything behind just remains the same. That's what we wanted. So that's how this push function works as a this push function should be implemented so that we can make this queue into a stack, right? That's all. Now for the other functions, it's just really simple because we did most of what we had to deal with, like of converting a stack into a queue while appending the element. So now we don't need to worry too much about the other functions. For example, if we want to pop it and it should work as a stack, then we know that it should just pop off the first element, right? Whatever the top element is. So it will just pop off 12. By popping, it should pop off the element that was added last, right? So like I said, stack is last in, first out, right? So when I want to pop it, the element that was added last should get popped out first. So 12 was added last here, and it's actually at the front of the queue itself. So if we use the simple pop function for the queue itself, it will actually become a pop function for the stack. And the reason this happens is that all the like manipulation that we had to do to this queue, we already did in the push function. So now it's just simpler to implement pop. Similarly for top, it's the same thing, right? Because top is basically like just looking at the front element of the stack, the top element of the stack, but not removing it from the stack. So that's all. And empty is really easy, right? So empty, it doesn't matter what the internal element structure of this data structure is. All we need to check is if the queue has a length of 0 or not. So if the queue has a length of 0, then it's empty, and otherwise it's not empty. So that's all. I hope you guys understood how we implemented all the functions, especially the push function, because that is where the main concept of how to convert this queue into a proverbial stack or and to in fact an actual stack really matters. So yeah, that's all. Let's move on to the implementation part now.
For the implementation, the first thing I'll do is import collections, right? Because as I said before, I'm going to model the queue that I'm allowed to use inside the stack class as a DQ, right? So I imported collections, and in our init function, all we have to do is create this queue data structure that's actually going to act as a stack, right? So let's just do that. Let's just say that self.queue is equal to collections.dq and an empty queue. So this will just create an empty queue for us, and it'll actually create an empty DQ, but I'm just going to use it as a queue. So yeah, that. Now for the push function of the stack, as we discussed, the push function of the stack has to do two things, right? It should first append, it should first queue push or push this element that we just have x to the back of our queue, right? Which is normally how elements are pushed to the queue. And then it should cycle back all the elements starting from the first element of the queue uh, to the back of the queue. And it should uh, rotate all the elements from the front one by one till the back of the queue until we reach this x again, right? So what do we do for that? So that's really simple actually. Let's just say that q dot append, right, x. So that will append x to the back of the queue, which is the push function that we're allowed to do. So push to the back, right? And after this, I'll do this, that for I in range of length of q minus 1. And the reason I'm writing minus 1 here is that I want to shift all the elements that were before this last element that I just added behind, right? So I need to run this loop for only those elements, right? If I would have put for I in range length of q, it would have done it for all the elements. That's why, but I want to skip the last element that I just added because I don't want to push that to the back again, because that would just be a cycle and it would be like just there wouldn't be any change in the queue. So yeah, so all we do in this loop is that we store the popped element in a variable. So q dot pop left is basically popping from the front of the queue, right? Which is the function that we're allowed to do as a pop here. And once I have this, I'll just append it to the back of the queue. So q dot append a. So this loop will take every element currently in the queue except for the one that was just added and shift it one by one to the back of the queue, which is what we discussed in the algorithm on the whiteboard, right? So that's all we have to do, and that's all for the push function, right? We don't have to do anything else. We don't even have to return anything, so that's all. Now for the pop function, all we have to do is return the front element of the queue, because the front of the queue is actually the top of our imaginary stack. This queue is working as an imaginary stack, right? So the front of our queue is actually the top of that stack. So all we have to do is queue dot pop left and return this, right? That's all. And to for top, what do we do? So we can also use a peek function here, right? Peek from front. So that's what we'll do here. So we'll return q of 0, which is just looking at the first element, the top of the stack, is what we want to return here, right? And the top of the stack is the front of the queue, so we just return q of 0, right? That's it. And now we need to check if it's empty or not. So all we need to do here is that if q, so if q has some length, then we need to return false because it's not empty. Otherwise, we just return true, right? It'll go into this if statement if the queue is not empty. So if the queue is actually has a length of non-zero, it will go into this if statement, and in that case we have to say that it's not empty, which means it will return false. And here, so if it doesn't go into the if statement and return false, it will execute this statement, which is return true, which means that the queue is actually empty. So that's all. Uh, just the code is just that much, and yeah, this should work. So let's. Okay, I also forgot to do this. That we should write self here because again we're working inside a class, and this is object oriented. So let's just write self.q wherever we've written q, right? And that's all. I think that's all the places. Yeah, right here too. So yeah, that's all. Let's run the code now. Right. So it's accepted on the example test cases. Let's try submitting it. Okay, great. So yeah, that's all. That's all for this video. Right. Before that, let's just talk about the runtime and the memory that we've used here. So the memory usage is basically big O of n, right? Where n is the number of elements that you are adding to your data structure, because we're not using any extra memory here. It's only like we have to, in the worst in the best case even, we have to at least keep track of all the elements that have been pushed to this data structure that we're in, the stack, right? And that is what we're doing here. We're not adding any extra like memory or using any extra memory apart from that memory that we're using. So that is the best that we can do, which we've done here. And the time complexity for each of these functions, let's discuss that. So for pop, it's big O of 1, right? Because q dot pop left takes a constant time. For top also, it's big O of 1 because peeking into a queue takes big O of constant time. And this empty function also runs in constant time, right? So these three are pretty obvious. Let's look at this. So is the init function. Initializing this will just take constant time. Let's look at the push function, which is where actually we need to analyze the time complexity. So what are we doing here? We're first appending this x to the end of the queue, and then we're running this loop. So this loop goes through all the elements in the queue except for the last one that we've just added. So this loop will give a runtime complexity of big O of n, where n is the number of elements that is currently in the queue, or the imaginary stack that we're trying to create using this class, right? So yeah, that's it. This push function works in big O of n. Pop, top, empty, and init work in big O of 1, and that's basically the time complexity. Uh, yeah, so I guess that's all for this video. Thank you for watching. I hope it helped, and if you have any doubts, feel free to leave them in the comments. If you have any suggestions, please feel free to leave them too. Thank you, and bye.